The next talk is going to be given by Zhenguo Wu. Zhenguo Wu received his BS and MS degrees in electrical engineering from Columbia University, where he's currently pursuing his PhD. His research focuses on the design of silicon photonic-based interconnect and optically reconfigurable network architectures for AI compute system. Zhenguo.
All right, thank you, Hossein, for the introduction. Hello, everyone. My name is Zhenguo, and I'm a PhD student at Columbia University's Lightwood Research Lab under the guidance of Professor Ken Bergman. Today, I'll present our work on a silicon photonic accelerated memory pooling architecture for efficient compute resource allocation. The wide adoption of artificial intelligence applications has driven the demand for more complex and larger machine learning models. And to achieve higher accuracy and support more complex tasks, the scale of these large language models in particular has reached trillions of parameters, which requires terabytes of memory to store them. However, the total memory capacity per compute unit is scaling at a much slower rate. And this growing disparity between model size and GPU memory capacity introduces additional complexities in training and inference of large models. And in addition to memory capacity constraints, LLM workloads also exhibit varying arithmetic intensities across both training and inference, as this figure shows. Even within inference, the prefill and decode stages also differ in their computational and memory bandwidth demands. And as a result, these variations in arithmetic intensity lead to different memory bandwidth requirements for a given compute system, depending on its processing power. And current compute systems connect processing units to a fixed amount of HBM via short-reach electrical I/Os. And the placement of these HBMs is constrained by their massive pin count, limiting their placement to an area near the compute die. As a result, the number of HBM stacks is limited by the chip package size and die perimeter, restricting memory capacity scaling and also its ability to adapt to changing memory demands. And to address this problem, memory pooling has been proposed, allowing compute units to share a dynamic pool of remote memory units connected via a high-speed network. And in traditional memory pooling architectures, remote memory units are connected via PCIe-based I/Os and then electrically switched networks, which introduce bandwidth bottlenecks and intermediate buffering latencies. And as a result, these systems rely on local HBMs as high bandwidth memory suppliers and use slower remote memory units, such as DDRs or GDDRs, as capacity expanders for offloading only. And this hierarchical design reflects a critical trade-off here, where local HBM will offer high bandwidth but has limited capacity due to packaging constraints, while remote memory units provide higher capacity but has reduced bandwidth due to distance limitation. And to address this distance and bandwidth limitation, silicon photonic I/Os co-packaged with compute chips have emerged as a promising solution. And on this slide, we'll describe the two key enabling technologies behind our proposed solution. One, the embedded silicon photonic transceivers and the silicon photonic-based optical circuit switches. For the transceivers, we focus on microring resonator-based designs that enable massively parallel bandwidth through frequency comb-driven dense wavelength division multiplexing. And compared to electrical links, these optical links can offer much higher bandwidth density, much better energy efficiency, and are distance independent. There have been many demonstrations around different types of photonic integration in both academia and in the industry. Here, we show an example of our custom-designed embedded photonic I/O co-packaged with a compute unit to replace the pluggable optical interfaces. This I/O features an 8.1 millimeter edge width and can reach a total of 16 terabit per second bandwidth, which will be the main bandwidth supplier for our work. In addition to supplying high bandwidth, we also study how we can efficiently allocate these bandwidths across the network using optical circuit switches. While we do not assume a particular OCS architecture in this work, these microring-based switches could offer fine-grained wavelength control and making them a suitable candidate for building our large-scale memory pooling fabric. Using these technologies, our proposed photonic solution then explores directly integrating DWDM-driven silicon photonic IOs along the edges of the compute die. Architecturally, prior works have proposed replacing conventional electrical IOs on compute units with photonic IOs to enable higher escape network bandwidth. And this increased bandwidth, combined with the use of optical circuit switching, has been shown to improve the efficiency of collective communications in AI workloads by providing high bandwidth direct optical paths. And we have seen this type of link design on the previous slide, but we want to highlight here that these photonic IOs can already achieve much higher than HBM bandwidth density without the distance limitations, making them feasible to connect larger pools of remote memory units to increase capacity without sacrificing their bandwidth. And building on this idea, we'll propose using the compute die's shoreline width as a critical resource when designing our next generation compute unit architectures. Here we show a semi-disaggregated compute unit where part of the shoreline width previously dedicated to HBMs is now replaced with photonic IOs. We can extend this to a fully disaggregated compute unit where all HBMs are replaced with photonic IOs. And if we assume a 120 millimeter available compute die shoreline width, it could accommodate up to 15 IO chips, achieving a total injection bandwidth of 30 terabyte per second. This design then creates a unified high bandwidth communication domain for both memory and network data movement. And we'll see how this works in the next few slides. To this end, we present the Silicon Photonic Accelerated Memory Pooling Architecture, or CPAM. In CPAM, compute units directly embed high bandwidth photonic IOs along the compute die's entire shoreline perimeter, fully replacing HBMs and high-speed network interfaces. Each photonic IO features a 3D integrated electrical integrated circuits and PIC connected through flip chip bonding. And for the memory pool, we propose integrating multiple memory units on a single chiplet to match the bandwidth of one photonic IO, following the similar concept of the previously proposed optically connected multi-stack HBM architecture. And under this design, the number of photonic IOs that can be integrated per compute unit is parameterized and by dividing the total shoreline width by the edge dimension of a single photonic IO. And the number of remote memory units connected to a photonic IO is then determined by the ratio of the photonic IO bandwidth to the per memory unit bandwidth. Each photonic IO can then be flexibly allocated for either memory access or network communication. And this is done by adopting a CPAC physical design, replacing traditional electrical packet switches with optical circuit switches in a B-cube physical topology. We note here that the rail-only topology is a two-dimensional variant of this design, and the OCSs can then dynamically allocate bandwidth across compute and memory units by using a one-shot reconfiguration strategy per workload. Additionally, CPAM adopts the intra-rack resource disaggregation model for a bounded increase in memory latency. For the memory pool, while we do not specify a particular memory interface, CXL is an example memory semantic interconnect technology showing promise for future adaptation to optical communication. And we also note here that a recent work on CXL interface has shown that the increased memory latency from disaggregating or memory pooling can be effectively mitigated by increase in bandwidth under a fully loaded memory system, which will be our key assumption underlying this work. Next, we describe our proposed optimization methodology to dynamically allocate compute resource memory capacity, and memory bandwidth using the analytical roofline model. The roofline model considers both hardware compute intensity and workload arithmetic intensity. Here, hardware compute intensity refers to the required number of floating point operations per byte of data loaded from memory to keep the cores fully utilized. In contrast, arithmetic intensity represents the actual number of flops performed per byte of data loaded from memory for a given workload. And the system performance under this model can then be determined by the lower of two factors, the hardware's peak flops performance or the product of memory bandwidth and workload arithmetic intensity. And as shown in this roofline plot, workloads with arithmetic intensity lower than the compute intensity are memory bound, as their performance is constrained by the memory bandwidth, whereas those with higher arithmetic intensity become compute bound, as their performance is limited by the peak compute flops. And we observe here that the optimal operating point occurs when arithmetic intensity matches compute intensity, ensuring that both compute and memory bandwidth are most efficiently used. And since memory bandwidth in the CPAM architecture is a reconfigurable parameter, our approach involves designing the hardware such that the compute intensity aligns with the arithmetic intensity to achieve optimal configuration for any given workload. Now let's walk through a more illustrative example of how this works. So, given the peak compute flops and then the workload arithmetic intensity, the minimum required memory bandwidth to achieve a balanced system can be calculated by dividing the peak flops by the arithmetic intensity. And the intersection of the two rooflines corresponds to the ridge point on the roofline plot, which we'll assume to stay invariant with increasing network size. Then, each memory unit in the memory pool provides a fixed bandwidth, allowing us to determine the number of required memory units to meet the minimum required memory bandwidth demand. From this, we can then determine the number of photonic IOs needed for memory access by dividing the total memory bandwidth by the per IO bandwidth. And now that each compute unit is attached to a fixed amount of memory, we can then estimate the number of compute units required to deploy the model based on the total workload size and the memory available per compute unit. We'll then exhaustively search through the parallelization design space and determine an optimal parallelization configuration. And depending on this chosen parallelization strategy, the arithmetic intensity, memory capacity, and bandwidth requirements may change. And in such cases, we revisit the previous steps to adjust the configurations accordingly. And this iterative process continues until a stable configuration is achieved or hitting a predefined iteration threshold. Next, we evaluate the performance of our proposed CPAM architecture using an analytical deep learning framework called Calculon. And the evaluation here focuses on transformer-based LLM workloads with their arithmetic intensity and capacity requirements profiled using Calculon. For our baseline configuration, we follow Calculon to model the NVLink domain for scale-up network and InfiniBand domain for scale-out network. For CPAM, we again model the CPAC network architecture with the amount of compute, memory capacity, and memory bandwidth determined by our co-designed optimization algorithm. As for our hardware compute setup, we model 3 generations of NVIDIA GPUs with varying compute and memory capabilities. If we assume that GPUs in CPAM are modeled with the same compute power as the B100 GPU, but with photonic integration, where each photonic IO occupies 8 mm of edge width, CPAM is then able to access significantly larger memory from the memory pool. Quantitatively, this sums up to a total of up to 720 GB of memory capacity and 30 TB per second bandwidth per GPU. And for our network scaling, we assume a cluster of up to 1,024 GPUs. And the table below here shows the total compute and memory resources in this cluster, highlighting CPAM's ability to deliver more than 3.75 times more memory resource compared to the baseline case. Next, we'll show our evaluation results. And in this first experiment, we compared CPAM against the baseline system on a variety of Megatron-based models with varying sizes. And the compute systems used up to 256 GPUs for training in the cluster. From the flops per byte plot on the left, we observe that CPAM's compute intensity closely tracks each workload's arithmetic intensity. And in contrast, the baseline compute intensity remains constant across different workloads since its compute to memory bandwidth ratio is fixed. And the figure on the right here shows the normalized iteration time. And where we observe that CPAM is able to consistently outperform the baseline architecture by optimally allocating the needed amount of resources based on each workload needs. And this results in up to 3.5x reduction in iteration time for training. We also observe that our approach is particularly effective for memory-bound workloads, as it can provide additional memory bandwidth to satisfy the memory requirement that the baseline systems cannot provide. Similarly for inference, CPAM is able to track the arithmetic intensity and achieve up to 3.5x reduction in iteration time. We note here that inference in general is more memory-bound and therefore would benefit more from increased memory bandwidth as compared to training. We next evaluate CPAM's performance under constrained compute resources. Specifically, we study how memory utilization and iteration time are affected as the number of available GPUs in the cluster varies. Here, we consider two representative workloads for training, the GPT-3 175 billion parameter model and the Megatron 1 trillion parameter model. For GPT-3 175B, we varied the cluster size from 16 to 128 GPUs. And for Megatron 1T, we scaled the cluster size from 128 to 1,024 GPUs. In the baseline cases shown on the two figures on top, the red cells indicate configurations where no feasible parallelization strategy can accommodate the model given the available number of GPUs. And these infeasible configurations, as we observe, become more frequent with smaller cluster sizes and with older GPU generations due to limited memory capacity. And among the feasible cases, darker shades represent high iteration time. And we observe that for a fixed GPU-HBM combination, iteration time decreases as the number of available GPUs increases due to an increased aggregate compute resource. In contrast, CPAM, as shown on the bottom two figures, consistently enables feasible configurations across a wide range of cluster sizes and compute generations. Notably, CPAM supports configurations that are entirely infeasible in the baseline case otherwise. And this is because, compared to the baseline case, which has a fixed memory capacity per configuration, CPAM is able to allow memory capacity to vary across configurations based on workload and system requirements. And these results then highlight CPAM's ability to improve compute utilization by providing sufficient memory capacity to expand the parallelization design space and also increase the likelihood of the system to accommodate larger models and identifying more optimized configurations. We next evaluate how CPAM scales across successive generations of compute and memory technologies. For compute, we here again model 3 generations of NVIDIA GPUs. And while each GPU generation is typically paired with a corresponding HBM generation, as seen in our previous experiment, here we also explore cross-generation pairings to assess the performance impact of decoupling compute and memory technologies. We fix network size here to 128 GPUs and run the GPT-3 175 billion parameter model. These figures on the left here show the iteration time for various combinations of compute and memory unit pairings for both training and inference. We first observe that for each GPU generation, performance improves as the memory generation advances in the baseline case, reflecting the benefits of increased memory bandwidth and capacity. Similarly, newer GPU generations outperform earlier ones due to higher compute throughput. And we observe that CPAM is able to consistently outperform the baseline as compute capability increases. This is because CPAM can provision more memory bandwidth that matches the increased compute demands through more optimized photonic I/O bandwidth allocation. However, within each GPU generation, CPAM's performance remains relatively stable across HBM generations since its effective memory bandwidth scales with photonic I/O bandwidth rather than being directly limited by the physical HBM bandwidth, as is the case in the baseline systems. We next examine how the system efficiency scales. And in this experiment, we scale the batch size for Megatron 1T to span a broad range of values. And we use iteration time and system efficiency as the error evaluation metrics, with system efficiency defined as the ratio between compute time and total iteration time. This figure here on top, or this figure entirely shows system efficiency on top and iteration time on the bottom as a function of batch size. We observe that across all configurations, CPAM is able to outperform the baseline in both efficiency and iteration time. Particularly at smaller batch sizes, both CPAM and the baseline case exhibit lower efficiency due to the workload performing relatively fewer flops per byte of data loaded from memory. And this limits compute utilization as the system is unable to supply the needed data to keep the compute fully utilized. And therefore, the performance in this low arithmetic regime is constrained by memory bandwidth rather than peak compute performance. And because of this, CPAM achieves higher efficiency as compared to the baseline case by provisioning more memory bandwidth to compensate for the lower flops performed. This results in efficiency improvement of up to 5.16x for A100 and 5.46x for B100. Moreover, with newer GPU and HBM generations, CPAM's efficiency in the low batch size regime also improves, increasing from 35% for A100 to 70% for B100. These improvements are enabled by more effective memory bandwidth scaling through access to higher bandwidth remote memory units in the memory pool. Similarly, the bottom row of this figure shows that CPAM achieves lower iteration time than the baseline case across all batch sizes. And to highlight the difference, the insets in these subfigures presents the relative performance gains in compute throughput. And this improvement is especially pronounced on the B100 generation GPU, where the higher compute capability demands proportionally greater memory bandwidth. And CPAM now is able to address this demand through higher bandwidth photonic integration. We next analyze how photonic I/O bandwidth scales across GPU generations for both training and inference, using Megatron 1B and Megatron 1T as representative workloads. In this experiment, we vary the per I/O bandwidth from 512 gigabit per second to 16 terabit per second. This scaling translates to a total injection bandwidth per GPU ranging from 6 terabit per second to 192 terabit per second for A100 and H100, and from 7.6 terabit per second to 240 terabit per second for B100. And from these figures on the left, we observe that in general, iteration time decreases with increasing per I/O bandwidth. And an exception is observed for the A100 running Megatron 1B, where performance plateaus beyond a per I/O bandwidth of 2048 gigabit per second. And this plateau occurs because the A100's lower peak compute throughput has become the limiting factor once sufficient bandwidth has been provisioned to saturate its computational capacity. But again, these results confirm that for future generations of compute units with higher compute throughput, continued bandwidth scaling will be essential for maintaining system efficiency, and our proposed silicon photonic I/O solution will provide such a promising path to meet this demand. And in conclusion, we have explored a photonic solution to address memory capacity and bandwidth challenges in AI workloads. By integrating high bandwidth silicon photonic I/Os onto the compute unit and using flexible memory pooling, we were able to achieve efficient resource allocation based on workload demands. We can also reduce iteration time and then improve system efficiency as compared to state-of-the-art compute systems. Our future work here will incorporate cost and power modeling to evaluate the performance, cost, and energy trade-offs of CPAM, taking into account evolving trends in compute, HBM, and photonic interconnect technologies. We also plan to extend the roofline analysis based optimization methodology to capture both memory bandwidth and network bandwidth, which will enable more accurate system-level performance characterization. And finally, I would like to acknowledge the sponsors of this work listed here for their support. Thank you all very much for listening. I'm now open to take any questions you may have. Thank you.
Thank you very much, thank you for an excellent talk. As a reminder to the audience, please feel free to use Slack to pose your questions. I can see there are quite a few questions already. I'll read them out loud so that then you can answer and then you can see it yourself. The question from Sandeep Jain.
Oh, yeah.
For memory pooling, what are protocols being used, such as CXL? How many CXL channels are used for 30T? In your diagrams, I noticed 16 PIC links only.
Yeah, thank you so much for the question. Yes, exactly. We in this work have assumed a CXL-based memory semantic interconnect underlying our photonic technology. And you mentioned you noticed 16 PIC links only, and that is we have 16 links per PIC, but we can incorporate let's say more than 10 or 15 PICs per compute unit. And so the total number of links we have is going to increase with a multiplication factor with the number of PICs we have equipped along the entire perimeter. And the number of CXL channels will then be used to accommodate the total number of links we have in our design. Thank you. And
The next question is by Bob Lance. As I understand it, GPUs use caches and multi-threading to hide the HBM latency. Does that need to change when with the increased latency of remote memory pools? On the positive side, does a shared memory pool reduce the need for copying data between GPUs? Does this change the way collective operations and algorithms work? Does it affect workload parallelization strategies? There are multiple questions here, so you can just go in sequence and answer them.
sounds good. Yeah, thank you. Thank you. Yeah, and thank you so much for the great question. Yes, exactly. Well, I think to answer the first part of the question, does that need to change with the increased latency of remote memory pools? I think we wanted to basically leverage the exact same type of latency hiding techniques for our memory pool because, as we know, these kind of memory pools introduce additional memory latencies by having a larger distance as well as an additional layer of protocol overheads. And therefore, we would really want to leverage the current memory latency hiding techniques. And we have also noted in our work that a recent work on CXL protocols has shown that these increased memory latency can be very effectively hidden behind the massive bandwidth if you can provide these kind of bandwidth under a very fully loaded system, which is the case in our AI workloads. And then the second part of the question here asks about, yes, so does a shared memory pool reduce the need for copying data between GPUs? Yes, so we kind of envision two types of network modeling in our work. And the first type is exactly what this question is saying, right? Because now that we have unified all the memory access to a single pool, so instead of going through the networking layer to access another GPU's memory data, we can directly access the data through the direct links to the memory pool. And that will help reduce the need for copying data between GPUs. But then that will the downside of that is that you need to change your networking paradigm by basically redesigning your collective operation or the way that you do your collective algorithms. But I guess the second model then will keep our current state-of-the-art memory access and networking access separately, but with with the ability to switch between these two different types of data movement or I guess, for each given workload, such that you keep the simplicity of the current compute architecture, but you also get the added benefits of accessing a much larger pool of remote memories. Yeah.
Very good. The next question is by Norio Sato. Silicon Photonics I/O has 16 gigabit per second per lane. That is more than a normal HBM speed of 6 gigabit per second or so, which means some gearbox SerDes functions are implemented in GPU or EIC. How much latency increase due to gearbox SerDes is estimated compared to HBMs?
Yeah, thank you very much for the question again. So if let me see if I can go back to my earlier slide. Right. So as we have shown on this slide, we have exactly like you said, photonic IOs with 16 gigabit per second per wavelength is more than the normal HBM speed of 6 gigabit per second per pin, and therefore we have assumed or a for our memory pools, right? We assumed that we can integrate multiple memory units or HBMs on a single chiplet to match the bandwidth of one photonic IO. And therefore, the total memory bandwidth accessed through one particular photonic IO will be the aggregate of multiple HBMs alone by themselves, right? And but again, we also to do this, we also need to introduce some kind of protocol overhead, and we have assumed a CXL-based design for this. And I'm not too sure about the actual number of latency increase due to this overhead as compared to the HBM latency. But I would imagine, for example, for CXL-based overhead, we can add about 20 to 50 nanosecond of additional latency for these metrics.
Next question is by Bob Lance. Uh, is this a study using an analytic model? Are you planning additional evaluation using simulations and hardware?
Yes, that's a great question. Thank you. Yes, we have only used an analytical model for this, which is the calculus as you mentioned. And yes, we do have plans to carry out further evaluations using more accurate memory level simulations and also put this into real practice in our test bed as well. Thank you.
All right. Next question is by David Chen. Can we use memories other than HBM in the memory pool, for example, LPDDR5X?
Yes, exactly. So I think the key takeaway from this design is that we have proposed a quantitative methodology to to approach this memory pooling architecture. And therefore, both the compute and the type of memory units we use, right, can be flexibly decoupled, which means that you can use any type of memory units you have or you need, as long as it satisfies the optimization algorithms methodology. And therefore, yeah, the short answer to that, yes, you can use any type of memory units as well as any type of compute units you need. But as long as you follow the methodology that we have proposed to optimize for the optimal amount of compute, memory bandwidth, and capacity that would satisfy your need based on your workload requirements.
All right. We have time for one last question
Mhm.
from Norio Sato. Flexible allocation of memory enables the rest to be used by other jobs. How do you think about the scheduler to assign other jobs with starting in different timeline? Otherwise, that may result in stranded memory problem.
Right. Yes. Thank you for the question. I think there have been a lot of other works that have explored the stranded memory problem elsewhere. And in this work, we, as for now, assume a maximum number of HBMs provisioned to satisfy the entire cluster's memory needs as a whole. And as you mentioned, let's say if we have a multi-tenant type of workload, we would always we will always be able to satisfy the maximum required amount of memory bandwidth, and to think about how we can handle the stranded memory in a multi-tenancy problem where we won't, for example, sorry, the workloads won't need to access these amount of memory will be our future work.
Thank you very much. We're already over time. Thanks for the great talk and answering the questions. I'm sure that Zhengu would be happy to answer the rest of the questions to the Slack channel directly.
Yeah,
Thank you
thank you
all.
very much. Yeah, thank you.